Perseverance rover and Ingenuity helicopter, the Mars 2020 mission, landed on Mars in February of 2021, joining two existing missions on the Martian surface. It landed on the northwest slopes of Jezero crater, which itself sits on the northwest slopes of the large Isidis impact basin. Mars was likely much wetter billions of years ago. Jezero crater was once flooded and now holds the remains of an ancient river delta. That all makes it very interesting as a place to look for organics and signs of past life. But our interest here is the modern environment and learning what controls sand motion, dust lifting, and dust storms on Mars. These two movies showed dust devils, vortices made visible by the dust they raised from the surface, dancing across the crater floor. The movies were taken by the Navcam cameras, and Marscam Z has also captured many images of dust devils, often when we weren't even looking for them. We are also able to make many measurements of vortices and dust devils using MEDA, the Mars Environmental Dynamics Analyzer. MEDA has a whole range of sensors able to detect a vortex passing the rover. There's a strong pressure drop, a slight peak in air temperature, a very strong increase in wind speed, and a complete change in wind direction when a vortex passes over. MEDA's radiation and dust sensors are also able to track a dusty vortex, a dust devil, over the rover. In this case, as a dust devil approaches, the LAT2 lateral sensor sees more scattered sunlight. Then as the dust devil passes away on the other side of the rover, the LAT4 sensor also sees more scattered sunlight. And as the dust devil passes over the top of the rover, the top sensors, the upward-looking sensors, see less downward sunlight as the dust devil passes over and blocks the sun. We find that at least 4 vortices pass the rover every sol, with at least 1 per hour in the early afternoon. This makes Jezero crater one of the most convectively active sites we've ever visited on Mars. We also find that more than 25% of these vortices are significantly dusty, which means that Jezero crater has far more vortex-driven dust lifting than observed by Curiosity or InSight. Now the puzzle is that InSight has similarly high vortex activity compared to Jezero, but unlike Jezero, sees few to no dust devils. The question of why is something that we're still trying to work out, but it may have something to do with surface properties at both sites. MEDA, NavCam, and SuperCam are also able to give insight into a different kind of dust lifting event. These rare, sometimes huge gust lifting events are driven by winds and not by dust devils. The central movie here shows a dust lifting event driven by wind gusts that covers an area of more than 4 square kilometers. We can put MEDA's wind observations in context by comparing with model predictions of winds across the entire region, where here the red cross shows the rover's location inside Jezero crater. We find that during the daytime, winds in this region are dominated by thermally driven upslope flows on the large-scale slopes of Isidis Basin, producing strong winds from the southeast and east-southeast. There's also a lot of variation in wind speed due to convection cells blown over the crater. However, in the evening, the wind direction reverses, and there are thermally driven downslope flows on the slopes of Jezero crater itself, although when these become strongest late at night, they don't extend to the rover's location. The observed wind patterns can explain modern Aeolian features, such as these wind tails shown behind rocks. The net sand transport direction, estimated from observed winds, which are dominated by strong daytime winds from the east-southeast, is consistent with the orientation of such features. However, there are other features, such as these ventifacts, whose orientation isn't consistent with current wind observations, and thus may show evidence of past wind regimes. Looking back at the model predictions for the daytime period, we can see these strong convection cells which cause peak wind speeds and variability in the middle of the day. We believe that the large gust-lifting events we observe are linked to strong wind gusts behind the leading edge of those convection cells being blown over the rover, and we can see here that MEDA was measuring strong wind gusts every 7 to 9 minutes shortly before we imaged the strongest gust-lifting event. On the same sol, we had microphone measurements and you can see that the microphone signal was saturated at exactly the same time that MEDA measured peak wind gusts. We can also look at modelled winds and dust lifting in a large eddy simulation, and you can see that the big peaks in wind speed at the edge of the convection cell are linked to a big gust lifting event, and you can also see small amounts of dust lifting by a dust devil. MEDA's RDS and TIRS sensors also provide downward and reflected sunlight between them. This allows us to measure the local albedo or surface brightness, which equates to surface dustiness. And we can see a drop in albedo after local dust lifting associated with a dust devil that passed over the rover on Sol 166. Using this kind of information, we can connect local dust lifting to local conditions that were needed to raise the dust. And in this way, we're able to learn the conditions that are needed to lift dust on Mars.